Hello, my name is Brendan Niddle, and this is my presentation of my honors capstone project that I completed as an undergraduate student researcher in the COTOV lab. My project specifically focused on the synthesis and analysis of antimicrobial chiral cerium oxide nanoparticles. So the question is, why are we concerned with the development of new antimicrobials? Antibiotic resistance is an increasingly growing threat that we're observing worldwide. More than 2.8 million infections occur in the United States per year in which the bacteria is resistant to at least one antibiotic. Globally, at least 700,000 deaths are attributed to antibiotic-resistant infections each year, which is a number that is likely severely undercounted. And it's projected that by 2050, that number could rise to more than 10 million deaths per year, which is more than currently die from cancer, and would make antibiotic-resistant infections a top cause of death worldwide. Perhaps more concerning is that the emergence of newly resistant pathogens is outpacing the development and implementation of new antibiotic treatments. It's not uncommon to see that a new antibiotic is introduced to the market and resistant bacteria pop up 1 or 2 years later. And due to the slow development of antibiotics, many underdeveloped countries are using last-line antibiotics at higher rates to treat infections, which could limit their effectiveness for the future. And we could enter kind of a dark age of medicine where we have these infections cropping up, but we don't have any treatments for them. And that would cause a lot of deaths that were, that are preventable if we could find a treatment for them right now. So one way that researchers are looking into developing new antibiotics is through antimicrobial nanomaterials. A nanomaterial is roughly defined as anything that has a dimension between 1 and 100 nanometers. They have the potential to revolutionize the medical field, and many applications of nanomedicine have already been proven. More than half of the world has already had nanoparticles injected into their body through the COVID vaccine. It uses a lipid nanoparticle to transport the mRNA used in its vaccine. So there's already been a proven application that has been used worldwide that has been proven safe. And that is one way that these nanoparticles can treat infections. The other way is that the nanoparticle itself could be toxic to bacteria. And the mechanisms of killing bacteria, if the nanoparticle itself is toxic, is generally unknown. There are general mechanisms that appear, but there still needs to be research into the more exact mechanisms of how they kill the bacteria. But one good thing about nanoparticles is that their properties can vary greatly depending upon their shape, their size, their charge, their chemical composition, meaning that you could, in theory, create a library of thousands and thousands and thousands of nanoparticles to dramatically expand the library of currently available antibiotics. And one great thing about nanoparticles is that they generally exhibit multiple killing mechanisms at once, meaning that the bacteria, in order to gain resistance, would have to develop simultaneous mutations to gain resistance to these killing mechanisms, which is a lot harder than just developing one mutation to combat a current antibiotic. Generally, new modern antibiotics are just derivatives of old antibiotics, meaning that all a bacteria has to do is mutate in a certain way just once, and it could develop resistance that way. Whereas with nanoparticles, they need to kind of coordinate multiple mutations, and if they're being random, it's a lot harder, and we would see that a lot less often. One thing the COTOV lab in particular is investigating is making inorganic nanoparticles more biomimetic. Biomimicry is the emulation of natural elements in the development of artificial systems and processes. This project focuses on biomimicry as a potential way to increase interaction between our nanoparticles and biological systems, particularly bacterial cells and biofilms. Of particular importance to the COTOV lab is chirality. Chirality is kind of it's a hard concept to explain through video, but generally it's a chemical in which it's not superimposable upon its mirror image. But more commonly, it's defined as having differential absorption to circularly polarized light. In the bottom left there, I provide the two kinds of polarized light, clockwise and counterclockwise polarized light. And in the top right, there's those three curves there, which represent the differential absorption of those two different kinds of light. The differential absorption creates that mirror image that you see in those graphs there. The origin of chirality is kind of vague and unknown, but the interaction with chiral molecules to its system is very important. One of the best examples is the Thalidomide Disaster, which occurred in the late 50s and early 60s, in which a German company was synthesizing morning sickness medication. And one of the kinds of medication would treat morning sickness. The other kind would actually attack the fetus and cause birth defects. The way they synthesized it, the mixture was racemic, meaning it contained both kinds of this drug. So you would sell that, and it would actually cause birth defects in pregnant women, which it didn't intend to do that. So they had to refine their synthesis technique to only create one of the types of the medicine that would treat the morning sickness. But that kind of highlights the importance of chirality in organic systems. So for our particular synthesis, we chose cerium oxide to be the base of our nanoparticles. Cerium already has been proven to be a biocompatible metal. Of importance is that cerium oxide nanoparticles are capable of removing reactive oxygen species from its solution. One of the mechanisms that nanoparticles use to kill bacteria is through reactive oxygen species generation. These reactive oxygen species are extremely toxic and actually will attack host DNA. So if you were to inject that into a person to treat an infection, the reactive oxygen species could attack their DNA and cause mutations and things like cancer. So we want to pursue more specific killing mechanisms that target just the bacteria, which is why cerium makes a good candidate, because we rule out the creation of reactive oxygen species. So we synthesized our cerium oxide nanoparticles using the wet precipitation method, which is a fancy term for just adding all the liquids together and having them react as one big batch. So we wanted to keep our reaction process as simple as possible. So it was all performed at room temperature, room pressure, under moderate agitation. We used a bunch of organic solvents. So sodium citrate was used as a chelating agent, and sodium borohydride was used as a reducing agent. The addition of sodium borohydride ensures that our solution would be more monodisperse. That is the goal. And it also creates the cerium oxide of the nanoparticle instead of it just being a cerium salt in solution. The reaction was allowed to progress for 2 hours before we stopped them. We washed them using isopropanol to precipitate all the nanoparticles, and we would then disperse our nanoparticle pellet into water and then freeze dry them to create a nanoparticle powder, which would then be used for analysis and testing on bacteria. We investigated 4 amino acid ligands. So there are 2 common ways to make nanoparticles chiral. One is you can hit those nanoparticles with polarized light and actually transfer the momentum of the light to the nanoparticle to make it chiral, or you can just attach a chiral ligand to its surface and you would kind of inherit the chirality of its ligand molecule. All amino acids are chiral. There's other chiral organic molecules like sugars, but amino acids present a very simple way for us to attach chiral molecules to the surface of our nanoparticles. The chiroptical activity of the nanoparticles was examined using circular dichroism, so that differential absorption of the polarized light. We also measured the surface charge and the size distribution profile using a zeta sizer machine, but we had some issues getting the exact size. So to get the exact size and morphology, we used electron microscopy. In the top right there, I have an TEM image of our nanoparticles. They're about 5 meters in diameter, so they fit the classification of a nanomaterial. And then in terms of our antimicrobial assays, we would fill 96 well plates with bacteria that would grow. We would at a relatively constant rate, so they'd be relatively the same rate between wells. And we would fill them with different concentrations of our nanoparticle and observe the level of inhibition between the different wells. We used E. coli and a strain of Aceraeus, which it was a MRSA strain, so it's resistant to types of antibiotics. So we can see if our nanoparticles would be effective against currently resistant bacteria. The results of that antimicrobial test are below. On the right there is the curve for the tests against E. coli. As we can see, there is either minimal or zero inhibition in its growth using our nanoparticles. On the left is Aceraeus, and we do see differential inhibition of our nanoparticles, but in general, we do see a general trend of inhibition using our nanoparticles. So the possible explanation for the difference between the amount of activity that we see between the 2 different types of bacteria is that E. coli is a gram-negative bacteria, whereas Aceraeus is a gram-positive bacteria. So we want to reaffirm that maybe that's what's going on here, that maybe having the different cell walls would attribute to different killing activities. So we, in the future, want to explore another gram-negative bacteria to test with our nanoparticles and see if they are still ineffective then as well. And then also, what's interesting is we observed the following killing activity. Glutamate inhibited the most, alanine inhibited the second most, and then cysteine and aspartate. Glutamate and aspartate belong to the same category of amino acid. So we would expect them to be very similar in terms of their activity, but as we can see, glutamate is the highest killing and aspartate is the lowest killing, even though they're very chemically similar. So it's possible there's something else going on in terms of how the killing activity is determined of our nanoparticles. That remains an area we want to explore more in the future. But also, in general, we observed the L amino acids killed greater than the D amino acid versions, which just goes to show, like the thalidomide disaster, that the L and D versions of certain molecules can interact with organic systems differentially. And then on the top right there is kind of a snapshot of a bunch of other different characteristics we were investigating as part of this project. One thing that's interesting to note is these nanoparticles are capable of sintering at room temperature and pressure. Normally, sintering can only occur at higher temperatures and pressures, but with nanoparticles and nanomaterials, they interact with the ambient thermal energy a little bit differently than bulk materials. So it's capable for a nanomaterial at room temperature to absorb a lot of thermal energy from its solution, even though it's only at room temperature. Because with nanoscience, things interact differently when we get that small as different, things that start to dominate at those levels. So it's possible to kind of elevate the temperature beyond what's normal by a bulk material standard. We're also investigating the possibility of doping other metals into the cerium oxide structure. And those three CD spectra that I provide, the middle one is the cerium nanoparticle by itself. The bottom one is cerium oxide nanoparticles. We can see the enhancement and emergence of new optical activity in these nanoparticles. And generally, the optical activity can translate to unique physical and chemical properties. So obviously, something gets enhanced or changed. We add this cobalt. It's possible they may be stronger antimicrobial as well. So that's something we want to look at in the future. But it just shows that these particles are capable of having other metals doped into their structure. Another thing we looked at, and this was another member of our lab group, was looking at attaching nanoparticles to the surface of aramid nanofibers. And he found that with our nanoparticles in particular, the strength was enhanced by a lot. I think with our nanoparticles, he found more than 5 times as much. And that's on the low end. We saw some results that were above like 10 times stronger. So that kind of shows an interesting physical property applied to other materials as well. There's also these nanoparticles exhibit a possible chiromagnetism, which means that the chirality can be modulated and enhanced using a magnet when you apply it. This has potential applications in the medical field. There are some researchers, we're collaborating with a research group from China, which is investigating using chiromagnetism to enhance the repair of bone and nerve tissue. So it's possible that our nanoparticles would have some kind of application there as well. And also, this reaction solution is sensitive to pH. This is something I found out myself on accident. I added too much sodium hydroxide to our solution and got that brown or orangish color on the right there, when typically the reaction solution is white. And I decided to test, okay, let's see if we just add different types of sodium hydroxide and sodium hydrochloric acid to these solutions. What do the colors look like? And it creates this spectrum of color that we kind of weren't expecting. And it's possible that the nanoparticles produced from these reactions are actually very different from each other. So we want to investigate to see, is there actually a difference in their properties at different pHs? Of particular importance is at the right there, at pH of 12, the reaction solution appears completely clear. This is before the addition of sodium borohydride, which normally is what we use to monodisperse and clear up the solution. So it's possible that if we react at a pH of 12, we might not need sodium borohydride in our reaction mixture. And that would be an interesting way to kind of ease this or simplify our reaction to make it even easier. So for the conclusions and the future directions this project can take, we successfully developed a easy synthesis method for the production of bactericidal cerium oxide nanoparticles. These nanoparticles exhibit a wide variety of unique physical properties, which in my opinion makes them an intriguing avenue for future research. In particular, we want to investigate the effect of pH, temperature, and removing the citrate from the reaction mixture. Generally, citrate is used to facilitate the binding of amino acids and other ligands to the nanoparticle surface. But when we remove the citrate, we observe negligible difference in their chiroptical activity. So if we could remove the citrate, it would just make our reactions and synthesis even easier for the future. Like I said before, we want to investigate the effect of doping the structure with cobalt, but we could also investigate doping with other metals as well. We also definitely want to investigate and quantify the ability of these nanoparticles to disrupt and prevent biofilm formation. Biofilm occurs when bacteria settle onto a surface and then produce a gel-like matrix that provides a physical barrier. So in the medical field, this is of particular importance because when you try to treat these bacteria using antibiotics, the antibiotics don't kill this bacteria because they're prevented by this physical barrier. Research into nanoparticles and other nanomaterials have proven that some nanoparticles and nanomaterials are capable of disrupting these biofilms. So if our nanoparticles are able to disrupt these biofilms, it would be another unique kind of property these nanoparticles have. We also want to investigate and quantify the cytotoxicity of these nanoparticles to mammalian cells. So as we said before, some nanoparticles exhibit a non-specific killing activity such as reactive oxygen species generation. So if we want to, in the future, apply these nanoparticles to killing or preventing an infection inside a human body, we don't want these nanoparticles attacking the human cells in the treatment of this infection. We also want to investigate more classes of amino acids. This could help us elucidate more of the patterns we're seeing and kind of see if we can draw more from a broader information just in general. The only issue with that is that it just is a lot of work to use that many amino acids and compare them apples to apples. And then we also want to explore alternative quantification methods of bactericidicity. One example of this is zone of inhibition studies. The way these work is that you make an even yard of bacteria on a plate, so that's even, kind of field of bacteria, and then you apply equal concentrations of your nanoparticle and then an antibiotic. You can kind of get an apples to apples comparison that way, seeing which kills that bacteria more efficiently. And we've been using this growth curve experiment because it provides useful information in terms of the kinetics of the killing activity. The issues we've had with this is that we've gotten inconsistent results using this method. Some days we'll see some nanoparticles killing better than others, and then they'll flip the other day. So it's kind of been a headache trying to get consistent results using those plate readers to observe this killing activity. And then moving on to the questions that are commonly asked for others honor students. I got into this project my freshman year. I applied to Europe and I got rejected. So instead, I'm like, I'm going to take matters into my own hands. And I emailed a bunch of different chemistry professors just to see, hey, do you have any openings in your lab? And Professor Kotov responded immediately to my email. He's like, yep, we have a position open if you want to start like next week. I'm like, sure, yes, next week sounds great. I definitely could have, waited a week or whatever to see if other people got back to me, but the Kotov lab was one of my top choices in terms of what I would like to get into. This lab explores both chemical engineering and a lot of biology, obviously, since we're working with bacteria. And that's something that I really wanted to do. I'm a chemie major, but I'm also a bio minor. I've really been interested in biology. So this lab was kind of perfect for fitting my interests. So if I had to recommend something for a future honor student, I would say, definitely weigh your options. But if a good opportunity shows itself, jump on that right away. And that's because what I found to be most useful, doing this project, the skills that I take away are those kind of skills that are learned by spending more time in the lab and getting more experience. Setting up a reaction, setting up an experiment, running the experiment, gathering those results and analyzing those results. That's something that, those are skills that you take to any research project, not just the one you're working on. And the more time you have, in research, the better those skills are going to be developed. So definitely, from my experience, more specific skills are not really going to be transferable, but these general skills of, learning on the job and getting more experience has been definitely helpful. It's going to help me in the future. So definitely, weigh your options, but if a good opportunity presents itself, jump at it because you will get more experience and be better prepared for the future. I believe that is all. So thank you.